Hi everyone, I'm going to talk about some of the data visualization research I did during my PhD in the computer science department at UC Davis. So first I'll talk about how air quality is usually visualized. If you look at Airnowgov, which is based on EPA data, they've updated the graphics a little bit on the site now, but basically you see this, which is an interpolation of the information from EPA air quality sensors, or you see a point estimate telling you which color it is in your location. And the contour map that you see here is based on an interpolation from that sensor data. So here's a map of where the sensors are. As you can see, the coverage is really uneven, but that's not really indicated by looking at the contour map. This is also a typical example of an air quality map. This is from Purple Air. I'm using data from these low-cost sensors in my research, and you'll hear more information about Purple Air later on. But basically in this view, you see each sensor reading, and the distribution again really varies across the country. So somebody looking at this map, maybe they'll kind of come up with their own interpolation in their head to estimate what the air quality is where they are. So right now, the intended design of something like this is to take a point estimate of the air quality where you are, and then you look it up in this table, which groups different air quality values into a risk level. So it'll say something like reduce outdoor activities or avoid them if you have respiratory diseases or something like that. But there can be a lot of uncertainty in these point estimates. For one thing, there's uncertainty in the air quality detections themselves, and there's also uncertainty in the interpolations, especially because the sensors can be really unevenly distributed. So here's an example showing different interpolated maps you could produce from the same underlying set of sensor readings. One of these sets of parameters that I'm showing is the one that's used on Air Now, and the other one is slightly different, but little assumptions like this can lead to a lot of uncertainty in the outcome. So I'm interested in whether people would make better or different decisions regarding air quality if they knew more about the uncertainty in the data. So thinking about how to show uncertainty in air quality maps, and whether that's even a good idea, I turned to examples in the visualization field of research on this topic. So hurricane tracks are an example of an environmental risk where uncertainty is really important. As the storm develops, there's a range of different model projections about where the storm is going to travel and how intense it will become. So in this case, the standard visualization you see here shows uncertainty in this cone, but it's really often misinterpreted. People usually feel like the cone actually represents the size of the storm rather than what it really is, which is a range of possible paths. So another option is to encode the uncertainty explicitly. So in this case, instead of showing the cone, you show every single hurricane path that the model puts out, or different models put out. So in this research, users are asked to guess, based on looking at these different tracks, what is the probability of the hurricane going in each different direction? So users were able to look at something like this and kind of identify the most probable path of the hurricane. But sometimes this isn't really the best design because it can be pretty cluttered if you overlay every single model output on the same map. So another approach is something like this, which is even more abstracted. It reduces the data down to a representative sample of the possible outcomes using an algorithm. So in this approach, the algorithm identifies kind of a representative set of possible hurricane tracks, and then each track is annotated with the size of the storm and intensity at each time step. So the authors of the study, they did an experiment testing different variations of this design, and they asked people to judge how much damage there might be at a certain point on the map. Okay, so let's bring this back to air quality. So in general, you can show different amounts of uncertainty, so ranging from a point estimate, which is what I showed earlier from Airnow, which has no uncertainty information, ranging all the way to an entire distribution of possible values. So dot plots are a particularly interesting option here. They show a number of symbols that's proportional to the probabilities of each of those different outcomes. So in visualization, there's recently been a lot of really promising research showing that using a dot plot to show uncertainty can really help people quantify the relative probabilities of different outcomes, and it helps them make more accurate decisions and often feel more confident in their decisions. So now I'll show some of the designs I came up with for showing uncertainty on a map of air quality. So first, the colors. Instead of using the standard air quality index color scheme, which you see on government websites, I replaced that with a perceptually uniform color scale. And that's a color scale where the amount of difference between each step appears the same to our eyes. I wanted to first include a couple of more standard air quality map views that don't explicitly show uncertainty. So the first view on the left, this is very similar to what you would see on Airnowgov. It's just an interpolation based on the sensor readings. The map on the right shows the same interpolation along with the sensors that it's based on. So this example includes both EPA sensors and purple air. So the next two designs are both based on this idea of dot plots, but transferred onto a map. So each 3x3 set of grid cells, and you can't see it too well here, but each set of 3x3 cells is colored proportionally by how likely each of those air quality levels is. So I won't really get into the technical details right now, but basically if you see a 3x3 group that has 3 light orange squares and 6 dark orange in the dark orange range. So I created versions of these grids at 2 different grid resolution sizes. And there's the fifth design is something that I'm calling small multiples, which is a term for any set of images that can be easily compared to each other. So here are, again, the 9 different possible outcomes of the air quality based on the same readings, but each one is mapped separately, ranging from the best case scenario to the worst case scenario. And on the right is the final design that I tested. I won't focus on this one too much here, but basically it takes the original contour map and overlays a set of lines that represent the 75th percentile outcome. So for this map, for example, you can say the light orange level of air quality is 50% likely to be contained within that orange colored blob, and it's 75% likely to be contained within those orange lines. So I performed a user study. People were shown each of these 6 views for each of 5 different sets of air quality sensor readings. So 5 different scenarios and 6 different maps, and each combination of those. So users were asked to imagine that they live and do activities within these circles. And so given this map of air quality, how likely would you be to reduce your physical activity outside? And I also asked people to think out loud as they answered these questions, so I could get more insight into how they were making their decisions. So I'll go through a few results quickly, and you can check out the paper if you want any more details. But in general, one takeaway is that people were more cautious about doing physical activity outside if they were shown one of the uncertainty views. And there are relative risk-taking level with and without uncertainty views. So the right 4 columns are the different uncertainty maps, and in general, people were more cautious when they had the uncertainty information. And another result is that users were also more confident in their answers when they were interpreting one of these uncertainty maps. And one possible reason for this is that people had to consider their decisions more carefully when they were making sense of this uncertainty information. They spent more time thinking about it, and therefore they felt more confident in their decision. So to analyze how people made their decisions, I annotated everyone's responses to the Think Aloud study, and I came up with this list of types of reasoning within 4 different categories. The first category is probability, which has to do with the chance of something happening, or the best or worst case scenario, or something that has some potential to happen. Appearance involves making judgments based on distances, sizes, and shapes, and other visual aspects of each map. Outside information means that they talk about information that's not encoded on the map, like other things they know, what might happen in the future, or how important it might be to them to exercise that day for whatever reason. And then finally, distrust includes any time people expressed doubt about the information that was shown on the maps, or when they had difficulty interpreting the map. So here are the results showing how often different types of reasoning were used for each of the different map types. And again, you can look at more detail in the paper, but I'll quickly go over a few conclusions that I kind of see in this plot. So first, when people only had no uncertainty information to look at, they often looked at things like the shape and the size of the blobs, the distance to a certain color, so visual aspects, and they mentioned how the air quality might change over time, hypothetically. And when we showed the contour plot with the sensors overlaid on top, the results really varied a lot. People tried to create their own mental interpretations of the data, and users most often expressed doubt in this case because they would notice how the sensor readings didn't always line up perfectly with the most likely interpolation. So this was subject to the widest range of interpretations based on people's own knowledge. With small multiples, which is showing these 9 different outcomes, a lot of people really liked this design. People talked a lot about proportions, how likely something is to happen versus not, or the best case to worst case scenario. And a lot of users were most confident with this view, and people often developed their own individual strategies for interpreting these maps, which was really interesting. And then finally, for these dot maps, people often used frequency-based reasoning, which is what I had hoped. They did it a little bit more often when there was a larger grid size. And people also made judgments based on how prevalent different colors were in the map. So again, kind of the proportions of different colors. And there was also a decent amount of difficulty interpreting these maps. I think there's more work to be done here, kind of optimizing the design, because for these maps, the right parameters to use, the right grid size, they depend a lot on the underlying data. So it might be really scenario or location dependent, kind of how to create one of these maps, but I think they're really promising. And that's it. Those are just a few high-level takeaways from my research. In general, I hope people keep studying how people use uncertainty visualizations and working on these designs. There's a lot of room for improvement and in our understanding of how people can use them. So thanks for listening, and feel free to reach out with any questions.